Welcome to Learning Outcome 4 on the theory and reactions of acids and bases. We'll look at what acids and bases really are, how the pH scale measures acidity, and the reactions that acids undergo. Across this outcome, you'll define acids and bases using Bronsted-Lowry theory and see how the pH scale measures acidity and alkalinity. You'll explain how acids react with alkalis, metals, and carbonates. Write those reactions as both full and ionic equations. Tell apart strong and weak from concentrated and dilute, and practice pH calculations using the formula pH equals minus log of the hydrogen ion concentration. Let's begin with ions in solution, because that's what acid-base chemistry is really about. Many acids and bases are ionic, or they dissolve in water to form ions, splitting into charged particles. Sodium chloride, for instance, gives aqueous sodium ions and chloride ions, and that little aqueous label means each ion is surrounded by water molecules. Those free ions are what let the solution conduct electricity, and at heart, acid and base chemistry is the chemistry of these ions. That leads us to ionic equations. A full equation shows every species taking part, but an ionic equation shows only the ions that actually change. Any ions that appear unchanged on both sides are called spectator ions, and we cancel them to reveal the real chemistry. Take hydrochloric acid reacting with sodium hydroxide to give sodium chloride and water. Strip out the spectators, and you're left with the ionic equation, a hydrogen ion plus a hydroxide ion reacting to give water. Some quick definitions. An ion is a charged particle formed by losing or gaining electrons. Dissociation is the splitting of a compound into its ions in solution. Aqueous just means dissolved in water. A spectator ion is one that's unchanged and appears on both sides of the equation. And an ionic equation is one that shows only the species that genuinely change. Now, the central definition of this outcome from Bronsted and Lowry. A Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor, where a proton is simply a hydrogen ion. So acids give hydrogen ions away, and bases take them up. When hydrochloric acid dissociates into a hydrogen ion and a chloride ion, the hydrochloric acid is the acid, donating its proton. The whole definition centers on the transfer of protons. This gives us conjugate acid-base pairs. When an acid loses a proton, what's left behind is a base, and together they form a conjugate pair. Take ammonia reacting with water, which is in equilibrium with the ammonium ion and the hydroxide ion. Here, water donates a proton, so water is acting as the acid, and ammonia accepts it, so ammonia is the base. The hydroxide ion is the conjugate base of water, and the ammonium ion is the conjugate acid of ammonia. Let's contrast acids and bases at a glance. An acid is a proton donor that raises the hydrogen ion concentration in solution. Examples include hydrochloric acid, sulfuric acid, and ethanoic acid, and an acid turns blue litmus red. A base is a proton acceptor that often provides or releases hydroxide ions. Examples include sodium hydroxide, ammonia, calcium oxide, and calcium carbonate, and a soluble base turns red litmus blue. It's worth being precise about bases and alkalis because the words aren't interchangeable. A base is anything that accepts protons and neutralizes acids. An alkali is simply a base that dissolves in water, and when it dissolves, it releases hydroxide ions into solution, as sodium hydroxide does, giving sodium ions and hydroxide ions. So all alkalis are bases, but not all bases are alkalis. Copper oxide, for instance, is a base, but it's insoluble, so it isn't an alkali. Now, strong versus weak acids, which is about how fully they dissociate. A strong acid dissociates completely into ions in water, as hydrochloric acid does, splitting fully into hydrogen ions and chloride ions, and we show that with a single arrow because it goes to completion. A weak acid only dissociates partially, like ethanoic acid, which is in equilibrium with its ions, so we use the reversible arrow, and most of it actually stays as whole molecules. Let's compare full and partial dissociation directly. A strong acid ionizes completely every molecule splitting up, giving a high hydrogen ion concentration for a given concentration, and we write it with a single arrow. A weak acid ionizes only slightly, just a small fraction breaking apart, giving a much lower hydrogen ion concentration at the same concentration, and we write it with an equilibrium arrow to show that most of it stays intact. Here's a distinction students often muddle. Strong or weak describes how fully an acid dissociates, whereas concentrated or dilute describes how much acid is dissolved in the water. They're completely separate ideas. You can have a dilute strong acid, like dilute hydrochloric acid, and you can have a concentrated weak acid, like strong vinegar. Concentration is just the moles of acid per cubic decimeter of solution, so don't confuse the two. Let's write a couple of dissociation equations. Nitric acid is strong, so it ionizes fully, and we use a single arrow. Nitric acid goes to a hydrogen ion plus a nitrate ion. Methanoic acid is weak, so it ionizes only partially, and we use the equilibrium arrow. Methanoic acid is in equilibrium with a hydrogen ion plus a methanoate ion. And as always, check that each side balances for both atoms and charge. And let's check your understanding so far. Can you state the Bronsted-Lowry definitions of an acid and a base? How does an alkali differ from a base? What's the difference between a strong acid and a concentrated acid? And why do we use a reversible arrow rather than a single arrow for a weak acid? Have a go before we move on to pH. Let's meet the pH scale. pH is a number that measures how acidic a solution is, and it depends on the concentration of hydrogen ions. The scale usually runs from 0 to 14, below 7 is acidic, exactly 7 is neutral, and above 7 is alkaline. The key relationship to hold on to is that a lower pH means a higher hydrogen ion concentration, and so a stronger acidity. To calculate it, pH is defined by the equation pH equals minus log of the hydrogen ion concentration, where that concentration is in moles per cubic decimeter and the log is to base 10. The crucial thing is that the scale is logarithmic, not linear, so each whole pH unit represents a 10-fold change in the hydrogen ion concentration. That means a solution at pH 3 has 10 times the hydrogen ion concentration of one at pH 4. A few terms to fix. pH is a measure of acidity, given by minus log of the hydrogen ion concentration. The hydrogen ion concentration is measured in moles per cubic decimeter. Acidic means a solution with a pH below 7 and a high hydrogen ion concentration. Neutral means a pH of exactly 7, as in pure water, and alkaline means a pH above 7 with a low hydrogen ion concentration. Let's find a pH from a concentration. Suppose the hydrogen ion concentration is 0.010 moles per cubic decimeter. We start from pH equals minus log of that concentration, so it's minus log of 0.010. Now 0.010 is 1 times 10 to the minus 2, and the log of 10 to the minus 2 is minus 2. So the pH is minus 2, which is 2. A pH of 2 confirms a strongly acidic solution. Now let's go the other way. Finding the concentration from a pH of 3. We start from pH equals minus log of the hydrogen ion concentration and rearrange it to give the concentration equals 10 to the power of minus pH. Substituting the pH of 3, that's 10 to the minus 3, which works out as 0.001 moles per cubic decimeter. And we can check. Minus log of 0.001 is 3, which matches the pH we started with. Real pH values aren't always whole numbers, so let's do one that isn't. The hydrogen ion concentration is 5.0 times 10 to the minus 3 moles per cubic decimeter, and we want the pH to 2 decimal places. From pH equals minus log of the concentration, we take the log of 5.0 times 10 to the minus 3, which a calculator gives as minus 2.30. So the pH is minus 2.30, which is 2.30. Let's read the scale as a whole. On the acidic side, below 7, the hydrogen ion concentration is high. pH 1 is a strong acid, like hydrochloric acid. pH 3 is a weak acid such as vinegar, and the pH falls lower as the acidity rises. On the other side, pH 7 is neutral, like pure water. pH 9 is a weak alkali, such as ammonia, and pH 13 is a strong alkali like sodium hydroxide, where a low hydrogen ion concentration gives a high pH. Time for some pH practice. Can you calculate the pH of a solution with a hydrogen ion concentration of 0.10 moles per cubic decimeter? Find the hydrogen ion concentration for a solution of pH 5. By what factor does the hydrogen ion concentration change, going from pH 2 to pH 5? And is pH 8.5 acidic, neutral, or alkaline? Work those through. Now let's turn to the reactions of acids, starting with neutralization. An acid reacts with an alkali to make a salt and water, and we call that neutralization. For hydrochloric acid with sodium hydroxide, the full equation gives sodium chloride and water, but the sodium and chloride ions are spectators and cancel, leaving the ionic equation, a hydrogen ion plus a hydroxide ion giving water. And that same ionic equation holds for any strong acid, neutralizing any alkali. Let's work through sulfuric acid reacting with potassium hydroxide. The products are a salt, potassium sulfate, and water. Balancing it, 1 sulfuric acid needs 2 potassium hydroxides to give potassium sulfate and 2 waters. In solution, the potassium ions and the sulfate ions are spectators, so we remove them, which leaves 2 hydrogen ions plus 2 hydroxide ions, giving 2 waters. Divide through, and that simplifies to the familiar hydrogen ion plus hydroxide ion, giving water. Next, an acid with a metal. A reactive metal reacts with an acid to give a salt and hydrogen gas. For hydrochloric acid with magnesium, the full equation gives magnesium chloride and hydrogen, and you'd see bubbles of hydrogen gas coming off. The chloride ions are spectators and cancel, leaving the ionic equation. Magnesium plus 2 hydrogen ions gives a magnesium ion plus hydrogen gas. In the process, the metal is oxidized while the hydrogen ions are reduced to hydrogen gas. Let's do zinc with dilute sulfuric acid. The products are zinc sulfate and hydrogen gas, so the full equation is zinc plus sulfuric acid, giving zinc sulfate and hydrogen. Checking the atoms, we've 1 zinc, 2 hydrogens, 1 sulfur, and 4 oxygens on each side. The sulfate ion is a spectator and cancels, which leaves the ionic equation. Zinc plus 2 hydrogen ions gives a zinc ion plus hydrogen gas, and the charges balance, 2 plus on the left and 2 plus on the right. Now an acid with a carbonate. Here, The acid reacts to give a salt, water, and carbon dioxide, and you'd see fizzing as the carbon dioxide escapes. For hydrochloric acid with calcium carbonate, the full equation gives calcium chloride, water, and carbon dioxide. The chloride ions are spectators and cancel, leaving the ionic equation. Calcium carbonate plus 2 hydrogen ions gives a calcium ion, water, and carbon dioxide. And bubbling that gas through lime water turns it milky, confirming it's carbon dioxide. Let's finish the equations with dilute hydrochloric acid reacting with sodium carbonate solution. The products are sodium chloride, water, and carbon dioxide, so the full equation is 2 hydrochloric acids plus sodium carbonate, giving 2 sodium chlorides, water, and carbon dioxide. Both reactants are aqueous, so their ions are free in solution, and the sodium and chloride ions are spectators that cancel. That leaves the ionic equation. 2 hydrogen ions plus a carbonate ion give water and carbon dioxide, and the charges balance to 0 on each side. Let's check your understanding of these reactions. Can you write the ionic equation for any strong acid, neutralizing an alkali? Name the gas made when a metal reacts with an acid and give a test for it. Write the full equation for magnesium carbonate reacting with hydrochloric acid. And explain why the ionic equation removes the spectator ions. Have a think before you move on.